Hello, Heritage Academy Geometry students, and welcome to another edition of Geometry, Seeing, Doing, Understanding. This is lesson 2.5, and as always, this video is brought to you by me, Mrs. Elzagary, PowerPoint, and the internet. If you haven't already done so, turn in your books to page 60, get that pencil out, get your Cornell notes ready, and let's get going. So as you know, we've been studying logic and critical thinking. Now, in this picture, let's look at the caption. My postulate that if flies taste good, then I taste good is apparently correct. So you can see here a smaller frog is getting eaten by a really big frog. And I want to draw your attention to that word postulate because that is the emphasis of our lesson today. Can you tell what it means based on this picture and caption? Before we go any further, let's explore our ultimate and intermediate objectives. We've been discussing throughout chapter 2 that our God is logical, and our Bible is filled with examples of this. Now, because God is logical and has a perfect plan for each and every one of us, He expects us to learn about, practice, and use this gift of logic. This gift is only given to us, and we need to use it with wisdom. Now, our objectives just for this lesson include explaining examples of how definitions of words can go in circles, describe the deductive system. We're also going to explore this concept of something called undefined terms in the study of geometry and how these terms apply to definitions. And we're going to define the term postulate. We're going to memorize and explain two important postulates, the first being 2 points determine a line, and the second being 3 non-collinear points determine a plane. Again, this is lesson 2.5, a deductive system, on pages 60 and 61 in your text. Now recall from previous lessons studying direct and indirect proofs. For a direct proof, it's pretty straightforward. We're going to develop a series of conditional statements. We're going to put those together in a syllogism where they go from one statement to the next. And finally, when we discover a conclusion, we can say that this is a theorem. Now, an indirect proof is a little bit different. Recall our hand of cards where we had these 4 tens in our hand. So we could probably assume then that no one else was able to have a royal flush. But when we make an indirect proof, we're going to assume the conclusion is false by saying, suppose that the conclusion is not. Then we're going to keep working those conditional statements until we find the contradiction. And then finally, we'll develop the desired conclusion where we state the false assumption and then say, therefore, this is true. Now, if you're in your book on page 60, you'll see this clever BC cartoon. And you see this gentleman looking up the word ecology. He reads that ecology means the cycle of life. So he goes ahead and flips over to the word cycle. And he sees that this means to move in a circle. So finally, he looks up the word circle, and it says to end up where you began. And so he thinks to himself, okay, I guess I need to go back to ecology. The idea of this cartoon is that sometimes words and definitions of these words end up bringing us in this circular pattern. So definitions are truly very important in mathematics because without these very precise definitions, a word can have different meanings. So we want to avoid the problem that we see in this cartoon. We don't want to come back to where we started. So in order to do this, we start with something in geometry called the undefined terms. And we're going to use these undefined terms as building blocks for every other definition in geometry. So think about some other words for a minute. Think about the words like the, of, a, are. You can see these words right here in this example from your book, and we use them all the time. But would it be easy to write a definition for the word the? Think about that, or writing a definition for the word of. These words aren't quite as easy to define, and yet they are building blocks of our entire system of language. So let's apply this now to 3 terms with which you're already familiar: point, line, and plane. These are our undefined terms in geometry. So you're thinking, we've already defined these, and yes, you're right to an extent. So let's back up and talk about what we know. We know Euclid says a point is that which has no part, and there is no dimension here, meaning there's no physical extent. However, we do have a location with a point. With a line, Euclid says this is breadthless length. We have one dimension when we have a line, and we know that if we have 2 points in space, we can have a line. Now, with a plane, we've talked about how this is a flat, unbounded surface extending in all directions. We know it's two-dimensional, and we know that if we have 3 points in space that are not on the same lines, we can have a plane. Now, by keeping the terms point, line, and plane undefined, we can give definitions to all other geometry terms using a common understanding of the undefined terms. So you've already seen in our first lesson of chapter 1 how these terms can be used to define other terms. We did this right at the beginning of class. So here are 2 examples that we worked on at the beginning. Example 1, points are collinear if and only if there is a line that contains all of them. In example 2, lines are concurrent if and only if they contain the same point. So for the same reason that it's impossible to define everything without going around in circles, it's impossible to prove everything. To avoid eventually coming back to the point from which we begin, we must leave a few statements unproved. These statements, called postulates, can then be used as a basis for building proofs and other statements. So a postulate is a statement that is assumed to be true without proof. So let's explore postulate 1. If I put a point on a coordinate grid, then can't I just take a straight edge and draw a line through it anywhere I feel? Absolutely. Could I, without a straight edge, draw a curved line? Sure. So what happens when I put a second point on this coordinate grid? Well, now I can take a straight edge and draw a single line straight through that, which gives me my first postulate, which is 2 points determine a line. So this postulate is suggested by the observation that if we draw a line, just 2 points are sufficient to locate its position. The word determine in the postulate indicates that if there are 2 points, then there is exactly one line that contains them. The postulate gives some meaning to the word line because for it to be true, it would seem that a line not only must be straight, but also must extend without end in both directions. Let's explore postulate 2. Now here you see points A, B, and C just placed randomly out there. So I can draw different lines using a straight edge to go through some of these points, and yet I really can't connect them with a straight single line. So because these points are non-collinear, the 3 of them together, we can put them in a plane. And this brings us to postulate 2, which is 3 non-collinear points determine a plane. So this postulate is suggested by the observation that although a line cannot be drawn so that it contains the 3 non-collinear points you see here, it's always possible to imagine that a plane contains them. The postulate gives some meaning to the word plane because for it to be true, it would seem that a plane needs to be flat and have no boundaries. So a postulate, remember, is a statement that is assumed to be true without proof. And we've just explored our first 2 postulates, which you'll continue to explore in more detail in today's lesson. But let's go ahead and review now how this entire deductive system works, because really all of these lessons are starting to culminate with this final idea of a deductive system. So we've discussed undefined terms, which really lead us to construct definitions of all other words in geometry. Using our undefined terms, not only do we have definitions, but we can also write postulates using direct or indirect proof. Now remember that if we're constructing proofs, whether it's direct or indirect, we are going to finalize them in a statement or a conclusion that we're going to call a theorem. And last, I want you to know that this entire system that has just been described, or this structure where we build these theorems logically, is called the deductive system. Did you get all that in your notes? If not, keep rewinding and going back for more. And I will see you next time in class.